why regression interactions were analyzed wrong. Try to convince him why he is wrong in his assertion. And so before I introduce you, I need to tell you that he likes to be interrupted, so don't hesitate. So I gave a longer introduction yesterday, so for those of you who didn't come to the Anastasi lecture, you're not going to hear the whole story. But just to tell you that Uri is a professor of behavioral science at ESADE University in Barcelona and affiliated with the Wharton School of Business, where he has been on the faculty for 13 or 14 years before. He has a PhD in social and decision sciences from Carnegie Mellon University, and he does work on human judgment, decision-making, behavioral decision theory, but is also at the forefront of work on alternative methods for methodologies to address the so-called replication crisis in psychology. Today, however, he's going to talk a pure methodological talk about interaction. All yours.
So I have 1 hour, is that right?
Well,
1 hour?
No, you can have 2 hours if you want.
No.
Can we vote on that?
No, we aren't voting on it. You can vote on it.
You have an hour.
I'll aim for an hour.
Oh, okay.
Okay, so thanks for having me. So this talk, yesterday's talk was the last time I presented that, and this is the first time that I'm presenting this. So there's probably going to be some glitches, typos, and so on, and the work is pretty much ongoing. And since I didn't know how much that would take, I have 2 papers just in case. This paper was recently accepted. It's very related. It's about U-shapes. U-shapes are about interactions with the same variable. So that's the effect change as the variable gets larger. So I may talk about that if I run out of time for this one. Or I may decide I don't have time for both. Okay, so the paper about interactions in one slide. What will I talk about? I would say there's huge problems with the way interactions are generally tested. You may ask, what do you mean by interaction? So let's say a researcher is interested in this question. Does doing homework increase test performance, especially if you're a boy? That especially if you're a boy is interaction, where gender is interacting with doing homework. And the way basically every single person tests that idea, they run a regression, predicting test performance, then you do homework, are you a boy, and then the interaction. And that makes a linearity assumption, assume everything is linear, and we always do that, and it's usually fine. It's usually not a problem in regression to assume linearity if things are not linear, because, and this is more important for my U-shaped paper, the regression is just the average slope anyway. So if the slope is it's a weakly line, that's fine. The regression will say what's the average slope for the weakly line, and we can still interpret that. That is not true for interactions, and it's been mostly neglected, that problem. So the false positive rate, meaning how likely you are to get an effect if there's no interaction whatsoever, if in fact gender does not influence how effective homework is, it's way more than 5% that you will reject a no. And then simple slopes is just hopeless, and you may ask me, what do you mean by simple slopes? Simple slopes is the way about maybe half of papers that have interactions report the results once they get the estimates. Once you get that estimate, you can say, well, if you do 7 hours of homework, or you do 5 hours of homework, you're a boy or a girl, how does it different things? And so you say, this is from a paper explaining it, if you're low in the moderator, this is the slope. But if you're high in the moderator, that is the slope. Okay, so that's the way it's presented. And I'm saying that is just hopeless. And by classics, I mean textbooks and very influential papers that talk about interactions. They do barely mention the problem that I'll talk about. Okay? That's why I'm referring to this, the multiple regression by Aiken and West. It has 39,000 citations. And this other paper on computational tools, so this paper right here, that's the one about the simple slopes that they made some code available, people use 4,000 citations. They barely mention that. So I'm going to try to give you the intuition for the problem. I'll think, okay, how do we solve it? And I'll propose 5 solutions. I'll do a horse race, which one does better? And I'll come up with recommendations. And my progress in this work is somewhere here. I'm not quite ready to make strong recommendations for everything that I want to make recommendations on. Okay, so if you're if you're a methods expert in the room and I'm saying something you think is wrong, interrupt me. And if you're not a methods expert and I'm saying something that doesn't make sense to you, interrupt me to ask for clarification. Okay, I welcome both kinds of interactions. So let me give you an intuition. Let's suppose men and women, the relationship between x and y is the log function. Okay, so all of us, whether we're a man or a woman, this is the relationship between x and y. It follows that shape. But we don't know that, because that's only God knows that. So we try to estimate it from data. We get some data. Look, I don't know if you see the tiny little gray dots here, gray dots there. Now let's code whether you're a man or a woman. And as it happens, for this useful illustration that I made up, all the men are here, and all the women are there. And so you estimate the regressions, and it's going to be, this is going to be the average slope for men, that's going to be the average slope for women. And so you would say, we had a super significant interaction, and this is the average slope for men, this is the average slope for women. Men who are high in X have a bigger return to in Y than women do. And you would report something like the regression for that. And you usually write something like, females are less affected by X than men are. But we know that's not true. We know all of them follow the log function. This is 80% of what I have to say, really. I mean, once you see this, like the floor falls under interaction interpretations. Okay? Let's make it, that feels very stylized. So let's make it slightly less stylized. Same log function, but now the data look like that. Okay, so here useful if you can read small font, it says the men distribution is a normal with a mean of 17 and of women is mean of 20. There's plenty of overlap, but men tend to be lower in X than women. And so men will tend to be this part of the curve and women will tend to be this part of it. Not all of them, but they will tend to. And you will have the same problem. So it doesn't have to be super stylized, incredibly unrealistic situation. Everybody some word? Happy? It's not just logs. Imagine you have a ceiling. Yep.
Can you back up for 1 second?
Yes.
I'm confused by fitted for the data and reported in the paper. Why aren't you reporting it as fitted? I mean, I think you made the same point there.
Yeah.
I don't understand how we
When I say as reported in the paper, is if you were to follow the simple slopes.
If you're using simple slopes, okay. So if you're just reporting it in the, let's say, traditional way.
The traditional way wouldn't have a chart. It would just say, P less than 0.01. Success.
Right. Well, you might have that chart, right?
I think it's rare to see. What happens is here, gender, it's a binary variable.
Yeah.
Well, that's controversial. But let's go.
Sort of, in theory, yeah.
For our purposes.
It's a categorical variable.
And so there it's easy, but if you were continuous, then you're kind of forced to dichotomize it.
No, fair enough.
Okay. No, it doesn't have to be log. It can be anything that's not linear. So let's say there's a ceiling effect. And men and women, now the mean for men is 22, the mean for women, for men is 19, for women is 22, so they're slightly shifted, so they're basically more women are being affected by this ceiling than men are, so it's affecting their slope more than men's slope. And it will look like that. Okay? So, alright, that's a basic problem. The basic problem is that regression tells you what is the average slope for those data, but what we wanted to tell us is what is the average slope at every point in the x-axis? What is the average slope? We wanted to answer this question, but that's not the answer. That's not the question the regression answers. The regression answers the average weighting by your observations. It's not weighting by the possible positions. So you have a lot of data here that women do. The average the regression tells you is going to have a lot of that, and the average for the men is going to have a lot of that. What we wanted to do somehow is to give equal weight to each x, so that it tells us the functional form that we're interested in. Okay? Okay. Yes.
It seems the figure as report as large one is also problematic because they ignore the range of the scores, right? Just focusing on the range on above 16 and then ignore the other part.
Sorry, which chart are you looking at?
The last part, the last graph, as reported.
This one, yeah, this one. This is it would be better in a paper. This, I just did a little quickly. I'm capturing the slope and I'm quickly putting it in a chart. If you did simple slope software, how would it do it? No, actually, it would still have the same problem. If you use the software, yeah, it would look okay. It would look at the mean overall, and one standard deviation overall, and one standard deviation overall, so it would be the same problem. So does that address? Okay. So I'm not the first to be troubled by this. I thought I was, but then I read the literature. No, plenty of people in the 90s, 80s, and 70s, or a few people, I should say, not plenty. So my favorite paper on this is by Ganza from 97. It's my favorite because it's the clearest. You read it and it's very clear of what's happening. It's not the best statistically, and it's not the first, but if you're going to read one, that's one I will read. He says, here's how he represents the problem. He says, look, imagine the world is like this. Y is x plus z squared. But you, as a researcher, are interested in interaction, and you don't control for z squared. And imagine that x and z are correlated. Then, when that happens, you can have a biased estimate of the interaction, because the effect of this thing is going to go there. That sounds, if you're a method person, that makes perfect sense to you. If you're not a method person, that sounds very confusing. And I think that's what people missed it. Because I think that is easier to get. These examples are easier. I see what's happening, and this is harder to grasp if you're not a methods person. But anyway, so he said that. And he said, the way to fix it is to add a quadratic. And so instead of estimating that regression, you estimate that regression, and then you're good to go. Okay? How influential was that? He wasn't ignored. He got 234 citations since '97. It's not bad. But this paper that I mentioned with the simple slopes, that just gives the software for it. Okay, and it's not even the conceptual, so you don't have to cite them, but you probably cite them if you did it. Has 500 citations in 2018. Okay, so it's safe to say that the vast majority of people who are doing interactions are ignoring Gansa and the people who came before him, are ignoring the yellow square. And before Gansa, there was Levinsky Harvey in 1990, and I don't think, I keep searching, I don't think it's being mentioned before 83, but probably somebody in the 70s and 60s did. I just haven't come across it. Okay, it's an old problem. Now, why low impact? Why aren't people paying attention? So one possibility is that this is one of those, and there's many of them in statistics. In theory, it's a problem, but in reality, we don't have to worry about it. Okay. And I'll show you some evidence that I don't think that's like that. I don't think that's the real reason. Another possibility is that it's been framed in a way that it's not sufficiently gray. It's like this is a problem, and I'm saying this is like the problem. It's like people aren't recycling some kind of plastic versus global warming. Okay, it's being framed as a small problem like plastic, and it's really more like global warming. So the truth, if you read the papers, they really look like this. Imagine the true model is quadratic. Then you need to control for it. That sounds very mundane. The way I would frame it is, if the reality is not perfectly linear, in any way, it doesn't need to be quadratic, log, whatever, in any way, then the interactions cannot be interpreted. So I think it's a much more serious frame. Especially there are fields that are entirely about interactions. Right? So there's a substantial share of publications in psychology. The key message is the interaction. The key message is dependent on this crazy assumption that everything's perfectly linear. Okay, how can we solve this? So we know how to solve, if it's not linear because of quadratic, we know how to fix it. Throw in a quadratic, but just like we don't know if it's linear, we don't know if it's quadratic, we don't know what it is. We don't know what the relationship between homework and grade performance in calculus 2s. Who would know if it's quadratic or log or whatever? How would you know that? But we could do it and say, well, let's just hope that it's fun and do the quadratic anyway. We could do splines and I'll explain later what that is. We can go the full tech mode, the generalized additive model, okay? And I will also explain that later. So as I'm working on this, I am trying very hard not to have to go here. Because when you read that, unless you're a methods person, it's like, oh, I don't want that. I don't want to deal with this, it sounds complicated. And as advanced as it is, it's hard to apply to any situation. If it's probe, if it's a structural model, if it's multi-level, it's hard to make it very general. So I'm going to try to avoid this, but I'll show you what happens with this. But this would be like the simplest. This is like 1970s level sophistication, and this is like modern sophistication. I'm going to see how sophisticated we need to get. The published papers propose this, but they are mostly thinking about quadratic, so it's natural that they say quadratic will fix it. I'm going to do a horse race, okay? I'm going to start with a true model. That's going to be like that. What do I mean by that? So it's going to be additive. It's going to be the sum of two things. It's going to be homework and gender, okay? Or parental location and income, whatever, two variables. And what I'll vary are is I don't want to think about a specific scenario. So I'm saying, let me just think about the range of possible things that could go wrong. So distributions are going to be, well, just the distribution where the effect is the noise and the sample size, okay? So in particular, let's say the functional form of x is linear, or it's quadratic, or it's to the fourth power, or it's log, or it has a ceiling effect. Okay, let's say f of x is like that, and f of z I'll do the same. Let's say x is normal, or skewed one way, or skewed the other way, and let's say z is normal, or skewed one way, or skewed the other way. And let's do two sample sizes and how correlated x and z are. Okay, so that's a zero correlation between x and z. This is x, this is z. These are data. This is the average relationship is 0, or a correlation of 0.5. Okay, so this led to 1,400 scenarios. So I imagine 1,400 different worlds where you want to run a regression where there's no interaction in none of them, because all of them are like that. Some functions, it could be, so to be complete, it could be x squared, y is x squared plus 5 of z. That's a function. So there's no interaction. There's 1,400 of those. And then I run the regression, and I do it 1,000 times, and I say, how many of them were significant? And so I'm running 1.4 million regressions and keeping track of the results. Okay. So for example, one scenario would look like this. I would say, well, let's make x skewed this way. Let's make z correlated 0.5 with it and be normal. Let's say x has a ceiling effect and z is like that. What happens if you run the model, right? So I'm trying not to be limited by my imagination, the kind of combination that could happen. So I told you that. And I ran the 5 models. Okay, what are the 5? The 5 models would be, one is the model we all run, the one you're taught in stats, the one that textbooks tell you to read, the one the software I have with 39,000 citations, the one everybody's using, just x, z, xz. Then the quadratic, then the splines that I haven't told you what it is. If you don't know, I'll tell you when it comes. And then the gamma model, the top-notch, state-of-the-art estimation. Everybody's on board? Okay. This is I'm going to show you a lot of charts like this. What I do is, there's 1,400 scenarios, and I show how many of them led to a significant result. It should be always 5%. And I sort it by from lowest to, so this may be, oh, this is log x, z squared, when one is normal, the other one is skewed, and you have 300 observations. We don't know which ones it is, we just pile them up. And so we say it goes like that. But that wouldn't be very exciting if that were true, actually. I'm just, so that's it. That's the actual set of results. Okay. So this is the model we all run. There's for like 140 situations, it's fine. Then it's problematic, and then it's forget it. So it gets really bad. What we want is a flat blue line on top of the red line. We want an approach to studying interactions, and no matter what you throw at it, it's going to tell you the wrong answer 5% of the time. Right? It's going to tell you something exists when it doesn't exist 5% of the time. That's what we're looking for. Okay. Okay, so this is state of the art. GAM stands for Generalized Additive Model. There's this guy Wood in the UK who's been working on this forever, maybe 15 years. He has a book. Everybody uses his R package, his MGCV. So if you're going to use GAM, you're going to use this. The way it works is you tell GAM, you tell this guy's program, you say, I'm interested in X and Z and possible interaction, but I don't want to tell you the functional form. You figure it out. And so it estimates any functional form combination that best fits the data with some penalty for not overfitting. So it's more sophisticated than splines. I'll show the splines later, because it makes sense rhetorically to go in that direction. Okay? So, but if you're familiar with splines, it's penalized splines that combine all of them at the same time. If you're not familiar with splines, it's kind of magical, and it finds a way to best fit the data, and you can really guess very weird functional forms really, really well. Right? So if you have a cloud of a scatter plot, and you want to know what's a right summary, like in Excel you could do it, and it will tell you a straight line or a quadratic. You will find anything. You can throw it a sign, and it will go like this, or ceiling, and then the ceiling ends, and it will figure it out. Okay. So I was expecting this thing to nail it. Okay. but it doesn't. It's a lot better, but it doesn't nail it. Okay. How are we reading this? So there's a bunch of scenarios here where there's about a 20% chance that the state of the art will conclude an interaction exists even though it doesn't exist. That's 4 times what it's supposed to be. That's not great. I was surprised by that. Are we still, nobody wants to ask any questions? We're still good? Yeah.
For me, I'm just like wondering, okay, what is the significance of this? Just looking at this portion and just kind of being like, okay, so like, how am I supposed to interpret like how much deviation is occurring like between the difference of your 5%?
Between those 2 lines?
Yeah, I just mean like, okay, well, where's the significant point of where it's like rising well above 5%? Like if there's a confidence interval or something like that, like how could I like then be like, oh, this is really significant?
Let me make sure I understand your question. Suppose I tell you I run not 1,000, but I run 3 trillion simulations.
Okay.
And I would tell you, that is the number as revealed by God. It's true. That's a true number. There's no sampling. There's no simulation error around it. Will you be content, or are you saying? Are you asking like a random noise question, or asking like a practical significance question? Like, are you saying is this gap big, or are you asking are we confident that gap is there?
The confidence.
We are very confident.
Okay, just because like the earlier situations I'm like don't feel as confident, and then as I go over, I'm like, okay, much more.
You mean like over here?
Yeah.
Yeah. So with to give you a sense. And so this takes a while to run, not crazy long, but it takes about a day to run the whole thing. And so once I'm set, I'll make it run instead of 1,000, 10,000, I'll just wait. But to give you a sense, if these were always 5%, the most extreme one should be 9%.
Okay.
Like if you try something 1,400 times, each of them with 1,000, it should be about, it's a lot higher than that. So this is abnormal, this should not happen.
Okay. Thank you.
Yeah. And so that's better. But it's disappointing, right? We're going for the most naive thing to truly state of the art. Something that's hard to explain. I don't fully understand the mechanics of the gum estimation. But it's not there. So I look at his book carefully, and I found this paragraph that says, you don't have to read it. It says basically, the p-values are wrong. Because we're fitting the data.
So,
Yeah.
I have a question.
Yeah.
So, I mean, the moment he says the p-values are wrong, then I understand his argument, because the p-values are all theoretical values that are based under the normal model. So if you have the dependent...
When you say normal, you mean Gaussian, or you mean like typical?
Gaussian,
Okay.
yeah.
Okay.
And so that's the basis for determining the p-value. They are based on an F distribution which follows from a normal distribution. But if you're simulating things which to begin with are
All over the place.
all over the place and not necessarily normal, why would you expect? That's a question of that's an issue of robustness of the test. How sensitive is the test to violation?
Yeah. So.
Yeah, you're not.
And I think that's the point he's making.
You're getting.
No,
screwed.
he's making a different. So he's making a different point.
Okay. He is, but I know what's happening.
Okay.
You're not going to tell
Solid.
them.
All right, it was
Okay.
nice having you here.
No.
What is happening?
All right. So the thing is that when you have a really skewed error distribution, the residuals can't possibly account for the ceiling or floor effect. In other words, the model is going to be constantly predicting something above the. If let's just say you have a ceiling effect, because the floor effect is exactly the same.
No,
The model is constantly going to predict it, and so the only way it can possibly accommodate for a ceiling or floor effect, if the error distribution doesn't know about the fact that there's a ceiling or floor, is to put it in an interaction. So I bet you what's out in your tail.
Okay. So I don't think that's right, but let's see if you. Let me show you things that do work. And when we get to them, you tell me, oh, yeah, that makes sense. Or
But the way to see if Jay is right
Yeah.
is to look at the 1,400 examples and identify those that are in the tail.
and I do that.
Okay.
I do, but I don't have it here. I'm in the process of doing it properly.
But this is.
But I don't think it's
What
about
he's getting at here is also the fact that there's going to be some overfitting, and hence.
So he says that's the problem.
Always a little bit wrong. Yeah,
He says that's the problem.
Yeah.
Because with the approach he works, it says it's try to best fit the data, but based on the data, and then you when you compute the p-value. So I don't think the problem is skewness or non-normality or ceilings. I think the problem is when you compute the p-value pretends that you wanted all along to find that particular set of cut points for your lines, But those cut points weren't planned all along. You plan them based on the data. So you're looking at the data and then you're testing on the data.
I think both things are going on now.
Okay, it could be. So when I show that, also you tell me if you update or if no.
Sure.
So he says that, and so I say, okay, if it's about looking at the data and then testing on the same data, let me fix that. I'm going to make the interaction not be parametric. So instead of doing that, so basically what the R package is doing is saying, let me allow X to be anything you want, let me allow Z to be anything you want, and let me the interaction be anything you want. I want to say, let's come down and only have those be whatever you want, and that's going to be a product.
Sure.
See if that makes, there's not going to be double dipping there. So and that worked. So the line I showed you before, the colors are not good. The line I showed you before is the red dotted line, and the blue line is the new line. So by making it less flexible, we gain that much. And maybe we could live with that, but I want to show you a bit better than that. Maybe we could live with that. That seems tolerable to me. What if we have less flexibility? So let's use your grandmother's cubic spline. Right? This is the 1970s spline. So now I'm going to explain splines if you haven't seen it before. Instead of a spline, basically, instead of saying there's one regression for all values of x, you say, well, this thing probably changes at some point, and so you have to tell it where to change. So I'm going to use a third. So basically, what is that saying? Is I'm going to say fit a regression line between the lowest point of x and a third of the x values, and it's going to be cubic, so it can be anything. But then I'm going to allow it to change between the 1/3 and the 2/3, and that can be any function also, and then any combination of the cubic, and then so that allows for detecting flatness. So let's suppose, let's say you're doing height and age. A spline would allow age to completely flatten out once you're 17, right? It would say age and height have this funny shape, it might be something like this. But then once you're 18, it's flat, 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 and then it kind of declines. A spline will allow you to figure that out in a way that a regression wouldn't. And this is not new. It's not used very much, but it's not new. It's, grandmother. So you don't need that, but if you use R and you're curious, this is how you do it. There might be in R. There's probably 3 other ways to do it. And so I'm going to have a cubic spline of X, the cubic spline of Z. I'm going to XZ to be like that. So I'm removing what Wood is saying is the problem, the double dipping. And that looks great. So now, good. Okay. The problem is, spline is an ugly word. It sort of scares people. So if you tell people, interactions are broken, do splines instead. If I say that, few people will listen to me, and I want them to listen to me. So I want to look for a simpler solution if available. But I know at least this is my backup plan. If I have this, is everybody on board?
Question. I teach this in my regression class.
Spline.
Yeah, absolutely.
Rip. How do the students react?
They're fine.
Okay.
Grandmother not bothered by it.
I'm not abused by the time yet.
So basically, in terms of the general additive model, what we're seeing is just like simple overfitting, right? 'Cause
Yeah.
It's so flexible, and so you're just removing that, and now you're parsing out and segmenting.
That's right.
Okay.
That's right.
Sorry, I just wanted to clarify.
Oh, you're good. Perfect. That's perfect.
So, but to do proper estimation of, so splines is essentially piecewise regression, because
Yes.
it's multiple regression, and the splines make sure that they connect at the right knot.
That's right.
Now what you did, you know ahead where the knots are, 1/3, 2/3. The real problem in estimation.
Wait, I don't know where they are.
So you fixed them in advance.
I fixed them,
Yeah.
but those are not the,
Yeah.
they're not the correct.
No,
What
that's,
GAM does is it finds those.
Yeah, it finds them.
okay, so that's the point I think not everyone understands, is that the complete estimation also needs to estimate
That's
the
right.
points where the pieces,
Yeah, it's a nice- so let's
where
be
the
exact.
beginning, so to speak.
So the difference between the grandmother's spline, or your class's spline, and
I'm not
GUM,
grandfather,
right?
I'm not offended.
Okay, is that, right. GUM says, well, why 1/3 and 2/3?
That's right,
And why cubic?
that's right.
That's arbitrary. Let's optimize it based on the data, and it does it in a very smart way.
Yeah.
If your goal is to look at to predict. If your goal is to predict, you should do GUM. But for the most part, we're not in the business of prediction. We're in the business of hypothesis testing. And so for hypothesis testing, it has a double dipping problem, and this simpler solution fixes it. So we have that. Okay, but I haven't shown you this one. Okay, no, I'm just messing. It looks pretty good. It looks pretty good also, and it's a lot simpler. Right? So if the goal is to get people to listen to me and say, hey, make sure to include a square term in your regression.
So that's your Ganza idea.
Yeah.
Okay.
Yeah, that's Ganzek and that's Bussmeyer and so on.
Okay.
But it turns out it works for. So they said if it's quadratic, you should do quadratic. And they said actually if it's anything, you should do quadratic. That's pretty encouraging. So we go back to your point. It's like you should be surprised by this. Maybe you're not, but you should be surprised. Like if you think it's about the errors and the normality and the whatever. X squared and z squared shouldn't help you very much. At least I was shocked when I saw it. I was not expecting this. This is such a wrong model. But it's, and I'll get to, okay, why does it work so well? Now it doesn't work. Yeah, so I will focus on this in maybe 3 minutes. I want to try to give, this is my intuition of why this model works so well. Okay, and then we can just share question. The quadratic is a way worse model than the gun model is. It's way worse. So why does it do better? Okay. So Legend 2013 says because the quadratic curves have perfect imperfections. Okay. So what is that? Why do they have perfect imperfections? When we add the x square, it's going to grab all the imperfection that is being grabbed by xz. Because if it's coming from the nonlinearity in x squared, it's better at it, at getting it wrong. So x squared is going to get it wrong, and xz is now free from it. Okay, so almost the way I think the intuition for this is all the wrongness in xz is picked up by x squared and z squared. It's not a good model, but we remove the wrongness that we cared about. That's that.
So, can I say? So my thinking is that it depends on what you think of as interaction. And so interaction is something which comes together in a synergetic or opposite way, which can only be explained by the joint impacts of x and y.
Okay.
Or x and z.
Sorry.
X and z. So what you need to do, you need to make sure that you clean and adjust and identify everything which is x by itself, and maybe it includes x squared, and z by itself, and only then what you're left with is can be properly called theorem.
So that's what I thought.
And
That's what I thought at first, but I don't think that anymore.
All right.
Okay. So I thought you need to get the model just right, so that the interaction will be right. But if that intuition were correct, the square model shouldn't work well, because are you getting the ceiling right with the square? No, you're not getting it right. You're getting it wrong in all sorts of systematic ways. But all the wrongness is captured by something else. It's like when you throw those sponges that grab all the color or something from the water and it's filled. It's like that. It's grabbing all the things that you should grab. It's still imperfect, but you're putting all the bad stuff there, and what you have left is a decent estimate. Yeah.
Well, one possible explanation is because x squared and z squared are correlated with xz, not just on the second order, but also with third and fourth order, I think from the Bussmeyer paper.
Yeah.
So that it will absorb some of the misspecification, not just on the second order, but with the third and fourth order, it may work better than GAN.
It's okay, I hadn't thought of that. So you're saying...
I doubt it actually works better than GAM. I think it works better on the p-value.
It works better on the p-value. Not if you want to...
Which is like the stupidest metric ever.
Okay.
Well, not the value.
The reason why I say that is because how do you interpret it? Could you actually make any sense of just a p-value?
So the way I would
psychologists try.
I would say two things.
They're wrong.
So I would say two things. I would say one, I think you can make sense of it. So you would say, look, there's some weird relationship. I don't know, but I want to know: do boys and girls benefit from homework differently? I think that's a question you can articulate, and I think a lot of people are interested in the answer. And I say, I cannot really tell you the magnitude, but I can tell you definitely boys benefit more from homework than girls do. And I think some people find, there's some value in that. But let's say you're not persuaded.
I'm totally not persuaded by that.
I want to fetch size estimation. That's what everything's about. that's it's my to-do list. It's literally in the output, but I haven't analyzed it.
Okay.
Because let me show you. Every dot here, every part of that line, it's basically 1,000 p-values where I ask, hey, how many of them are less than 0.05? For every one of those p-values, I have an effect size estimate. And it's basically some version of the average interaction between those two things. And I know the true average interaction. And so I want to know to what extent this is unbiased, if you were interested in that number. And I believe it's unbiased, but I haven't really, as I mentioned, I haven't done anything that I want to do. Suppose let's imagine that's true. Let's imagine it is an unbiased. Would you then be interested in the output? Or you still would say,
Depends. I don't know.
You don't want to
No, the reason why I say this is I tend to think that you have to know enough about the substance of the actual question and what sort of functional forms would likely be emerging.
Yeah, but I don't think you can meaningfully say. To what extent can you anticipate? Like, if I ask you, is there going to be a ceiling effect of homework on math performance? Is it probably? Is it within the range of probable values? You have no idea. And you said, and right before the ceiling, is it kind of concave and then convex, or we really don't know.
I think a lot of times you do know because you know a lot about the dependent variable. So, for instance, if the dependent variable is class score, you know that it can't go over, and it's very likely to actually have a ceiling effect.
Yeah, but I'm not thinking of that. I'm not thinking of a ceiling on the y. I'm thinking of the effect of the x on the y. So it could be that once you do 4 hours of homework, that's it. The 5th hour won't help. But if you talk to your classmates, it would help your grade. So it's a local ceiling. I don't know if there's a term for it. It's a local ceiling. So far I haven't modeled real ceilings. I've modeled only ceilings on the effects of the x and the. There's only so much you benefit from homework, but maybe other kinds of studying would help.
I get it.
Okay, let me.
I have a question.
Yeah.
So that was really stimulating, but so just in terms of
The statistician arguments.
just so I'm not lost, just in terms of, so for me, I'm always like, oh, p-values completely separate and independent from your effect size, just in terms of like, so, and I heard you guys speaking of like pulling out specificity and how that's related, but I kind of got.
Pulling out specificity, I don't think that's the correct.
I don't know, I'm just like
Pulling out
pulling words from a dialect that I heard that I didn't understand.
So once you have the sample size, once the sample size is fixed, so I have 100 observations. Now there's the p-value and the effect size are very closely related.
Oh, yeah. Okay. Yeah.
So I could map here instead of if I know there's a decent contingent of people who hate p-values, right? If they were the majority, and I was giving this talk, I would have plotted instead of share of studies that are false positive, I would have shown a magnitude of the bias or something like that. So the true effect is 0.
Mm-hmm.
How far do you get?
Mm-hmm.
And I think it will be a similar. You estimate as 0, and then bias increases quickly as you. And so that's the discussion we're having. Okay. We're saying, suppose somebody didn't care about p-values, would this actually be? Would the traditional one be wrong in terms of bias, and would this solution be good in terms of bias? I think it's very hard to get a flat line like this and be biased. I think it's very hard to get that. So that's why I'm very optimistic that when I do the analysis, it'll be unbiased, but I don't really know. Okay, so we did that. Oh, okay. So that's the intuition for why, that's my intuition for why it's working so well.
Before moving, kind of a quick question. Like you said y equal x plus z plus xy is equal to that. Then you add in the square of two terms.
Yeah.
Isn't really because of x square and z square got an effect, or simply increase the number of predictors, just the fitting the better?
It's neither. It's because you don't want xz to pick up any effect coming from nonlinearities in x. It's actually, just think of any regression. You say, I want to know the effect of age on height, but I want to control for gender. Because I don't want, maybe my sample, women are older, and so that's going to be confounding. So you say, I want to know the effect of, how does z affect x? But I want to control for the fact that when z is present, maybe x is higher, and when x is higher, the effect's different. Okay, so actually, let's make that more concrete. So let's say, you want to control for the effect of, okay, boys and girls, homework. And so you want another interaction. But I want to control for the fact that maybe girls who do homework, they do so much more homework that the slope is different, right? That was my very first example. So by throwing the square, you're trying to control for non-linearities in number of hours of homework. That's what. It's not because you think it's squared, and it's not because it's just another term. It's a term that captures. Let's call it like the construct of non-linear x. I want to control for non-linear x. What do you mean by that? Well, let's say it's x squared. So it's my attempt to control for non-linear x. GAM is also an attempt to do that. It's a better attempt, but it overfits. The spline is a better way, and it doesn't overfit, but it's complicated. It's more complicated than x squared, right? If you can run a regression, you can throw in an x squared. If you can run a regression, you're not necessarily able to run a spline.
Yeah, but could it be not only x squared is the like in this model? Could it be anything, right? Could it be depends on your data simulation? Could it be x, like a cubic?
No, so what you need it to be, you need it to be as similar as possible to the interactions. And because it's x times z, that's a square. If you had, let's say you had xz squared, then you want x to the fourth. Right? You want it to be of the same order, I think is the term. You want it to be the same order so that and maybe that goes back to the higher order, so to the higher moments. I haven't come with that. Maybe that's the reason. So I had the intuition that was very important. They had to keep the same order. But so, for example, if you were to, I haven't done this, but if you were to say cube instead of square, I think it would be a lot worse. Because it would even if it's truly cube, because let's say it's truly to the fifth power, right? Both would be wrong, but one would capture all the wrongness that xz can capture, while the other one wouldn't. It would capture other wrongness, and it would leave some wrongness for xz. Sorry, we're good? Did I get to it? Good. All right, so we're here. So Planck comes first, and Corey comes in this horse race. Remember, it's a horse race. Okay. So what I do now is I look at the difference between the spline and the quadratic. So 0 would be a tie. This is an arbitrary line I drew at 1%, because I said, look, do we really care about? I mean, I could otherwise magnify the y-axis, right? So I'm going to say this is basically the same. This is saying one has a 5% false positive rate, the other one has a 6% false positive rate. So many other things that will go. This ceases to be a first order problem. And it's now you worry about confounds and exclusions and so on. Okay. So we have this part. Can we understand this? What's happening here? This goes back to your point, David, about understanding it. And I've only started, and I haven't made progress. Okay. So there's something I'm referring to as dashboard charts that we first used for another paper. It's called specification curve, and they look like this. Okay. So they're supposed to be physically just below the other chart, and they tell you what operationalization is behind each result. So for example, let's say we had here the first dot of another curve. You would say that one came from a log of x with an x, or with an x to the fourth, or with a Silian mean. So this tells you which of the 4 operationalizations of x are you using. And then this blue line is telling you trends. So let me interpret this for you. It says, as the difference between the spline and the square get larger, the share of specifications that involve linear increases. I did this morning. I haven't thought about what that means. Okay, I'm in the process. But this is telling me where is this coming from. So if the chart is confusing, this is saying these specifications here are not log of x, are not x squared, are not x to the fourth. They tend to be x. Okay. And you can also see they tend to be the higher correlation and so on. And I'm trying to figure out why. The goal will be, is there a tweak for the quadratic? Or is there some sort of test you can do and say, if you're in a quadratic, you're good unless the following happens. I personally feel like if I was gun to my head, had to write the conditions today, I would say, do the quadratic in the main paper, and if you tolerate splines, put them in a footnote. That's what I would recommend. Not because I think splines are worse. in my paper, I'll probably display in the main paper. But I want to be persuasive, so I want to tell people the easy solution. The easy solution is a square, not a spline. Okay.
So, can
Yeah.
for just a second. So, what you're doing here, it's nice. I mean, this approach of specific, what do you call it?
Specification curve.
Yeah. But I think this needs to be supplemented, especially in the way you've done your simulation, by also correlating the level of discrepancy between the two top models with all the factors that went into your simulation.
With what, sorry? With
all the other factors.
Yeah, so run like a meta regression.
Multiple regression. We have variables for was they skewed to
Yeah.
the right, skewed to the left,
Yeah.
and so
Yeah,
on.
yeah.
And I think that that will also account for a variety of explanation that people have offered.
So the plan is to do that. The trick thing is, now you get meta. Do you expect the meta regression to be linear? What, you know?
Yeah, I understand. Yeah.
So like it's.
So that's why you have 1,400,000. So you don't have to
Yeah.
worry too much about.
Yeah, that's true. So the idea is to combine this more graphical approach with a regression, but that's in the to-do list. Okay, so what about power? Okay. I focused on the situation, so just an announcement, I will not talk about the second paper. We won't have time, okay? I've only focused on the situation where there's no interaction and everything you detect is false. Well, what if there is an interaction? How much are we suffering from using these better tools over the simple ones, okay? So I'm going to run the same kind of simulations, but I'm going to add a true interaction effect. And so it could be like that XZ, but that's cheating, because I'm assuming the world is just like I model it. So I'm going to do a lot of other things. I'm going to assume that the true log of fx plus fc. So here there's an interaction, because when this number is higher, the impact of fx is going to be smaller, just because it flattens out. And note that this is fx and fz, it's not x and z. So I'm going to take x, I'm going to square it. I'm going to take z, I'm going to log it, I'm going to sum them, and then I'm going to log that, right? So try to make it as flexible as I can do. What if it's the square root of xz? What if fx over xz? So the bigger z is, the smaller the effect of x, right? So flattens out 0. It's going to be the sum, but there's a ceiling over. Now it's a ceiling of the kind you're more familiar with, the ceiling overall, or a ceiling of the 75th percentile. To do that, and we have 2,700 scenarios now. One way to reduce the number, I only have one sample size. And so what I do is, I say, okay, it's going to be x squared, it's going to be log of z, it's going to be this. What sample size do I need so that the quadratic would have 50% power to detect the interaction? That's only my sample size. And I do all the models, and I repeat that for the 2,700.
Nice.
It's nice to have computers. Okay, so this is the chart, and again, very last minute. So all I would say is this one. All I would say is there's enough. Actually, I won't say very much about this. I was going to say it's going to be easier for us to interpret just the mean power. This is the distribution of them. Let's just look at mean power. It looks like this. Okay? This is way easier to understand. The previous chart needs a lot of work before it's ready for representation. So remember I calibrated sample size, so the quadratic would have about 50% power, and it's 48. And there's boring reason why it's not 50, but they're boring. Now there's the gun, and it's not a lot more. So if we're in p-value world, and we want to have power, we're paying a high penalty in terms of being wrong a lot, just to have that extra 10%. If this were 90%, I would say maybe we should develop good tests, or maybe we should improve the GAN model. But I'm saying, it doesn't seem like it's worth it. It doesn't seem like it's going to pay off to do it. It's so much more complicated. It's so complicated, it's only in R. In Stata and in SAS, they don't, well, I don't know about SAS. Stata doesn't have GAN, so you couldn't just use that. This is that tweak that I did with and this is the spline. Remember, the spline is slightly better than quadratic, and that's why the quadratic beats it on power, right? So the quadratic, it's a little bit more trigger happy. The quadratic is a little more like to say this is significant. That happens when it's nothing there, and it happens when something is there. And so that's there. So the summary, huge chunks of psychology and beyond, political science, economics, are all about the interactions. Everybody does this. that is almost never right. And adding x squared and z squared, you throw the perfect imperfections, and it kind of fixes it. This is slightly better, but this is good enough. And now I would talk about U-shape, but I don't think we should do that.
They said they wanted 2 hours, right?
I think you said that.
No.
Yeah, so I'm tempted to stop here. Maybe there's some questions. I'll address them.
Okay.
So I'm trying to reconcile this with the fact that I never seem to get significant interactions in my models, even when I think they should be there, and even when there's a logical reason, and I've got decent power. And my recollection from my non-psychometrics background is that interactions were always harder to detect than main effects. And yet, hearing this, I'm thinking, how come I don't always
Yeah, that's a
find
good point.
significant interactions?
Right, so there's an answer that's very good, but I don't think it's true. The good answer, is, oh, you must study linear models. Like your phenomena must truly be very well approximated by a linear relationship.
Is anything approximated well by?
Well, that's why I don't believe it,
Yeah.
because I don't think anything's really linear.
Yeah.
But that will allow me to.
And I would say that's not true. I mean,
Yeah.
I think
Well, I agree.
we're looking
I don't
at mental
think
health
that's true.
outcomes. Nothing's linear.
Yeah, I don't have a good answer. So I'm thinking, how would I address that? Maybe I should redo the simulation with the false positives, where the sample size, instead of being arbitrary, is set so the main effect, for example, has 80% power, and that may give you a
Which
less,
is what we usually base
you
power
try to do
estimates.
somehow, right?
Right.
And so it would say, I'm not sure, because it may be misleading. It may be misleadingly reassuring, but that is a valid point. Like,
Well, I mean, the related, I guess the related question is that
No,
because
sorry,
I do clinical research, we're always underpowered, no matter how much.
sorry, but I now have a better answer.
Oh.
That's purely mathematical that I do believe more in. It could just be that the things you're interacting are not correlated. Does that seem
Doubtful.
doubtful? So what kinds of variables are you talking about?
I mean, I do clinical psychology research,
Right.
so I mean, let's say we've got, mental health or historical factors about whether the person's had a history of mental health treatment, what their
Crossed
baseline with their depression score.
Yeah, so it's unlikely they're going to be.
Yeah, nothing's
Random.
uncorrelated,
Yeah.
right? They're all 0.3.
Yeah.
Yeah, but I
Okay,
guess
so
the
with
question is,
point-
does this matter if you're? I guess you just showed us an underpowered example, but with small sample sizes, or relatively small sample sizes, do you see the same phenomenon?
So I will take this look, if I wanted to calibrate my false positive simulations to be sort of realistic in some sense, it's nice to think of this a sample size that somehow makes sense. And I haven't done that. I chose arbitrarily 300 and 600. And so I will do that. I will do that.
I
That's a
think
fair
one of
point.
the things that probably saves a lot of models from interactions, how many variables did you use in your sense? How many predictors?
Oh, just those.
Okay, so what I think is often happening is that if you have 10 variables and you enter a linear model, chances are pretty good that a lot of those indirect effects are captured. There's actually a name for your quadratic model, which
Okay.
I had to think about. You're essentially running that's a second order Taylor series approximation
Mm-hmm.
of it, and when you put it
But the Taylor wouldn't have the
clarified-
XZ, would it? It would just.
It
be,
would because you'd have a second order Taylor series in both. It's a multivariate Taylor
Okay.
series. So what's wrong with the not including the x squared and the z squared? And until I saw the slide, and it was just like, oh yeah, of course it's got to be it. So, but I think so. If you look through the math, what's happening is that Taylor series would be asserting that those two pure quadratics would be equal to 0, which is why the standard interaction model is so wrong.
Mm-hmm.
It can't possibly be doing a good approximation to most interactions. But anyway, I think what happens a lot of times is if you have 6 to 8 variables, the linear model probably often does a pretty good job, simply because it's managing somehow to capture what those higher order terms would have been giving you
Yeah, so I'm thinking so one way to do that. So one thing I want to do is
There's
move
another thing
closer
I
to a
wanna
real
mention
data set.
Is there's a decomposition for interactions that the economists use called the Oaxaca Blinder Kitagawa decomposition, which
The well-known.
Yeah.
well known among economists, but it's
Wait, Oaxaca, is that a last name or is that?
that's his last name.
Just sounds good.
It's one of those things that was reinvented by 3 different people, so the names were tacked
And what else
on.
do we do?
The first person to invent it was a demographer named her last name is Kitagawa, but it usually goes by the Oaxaca decomposition. But that's for a discrete variable like gender, and the whole point of it is it takes into account all the dependence among all the regressors. I have a feeling that's just my
So
hunch.
I will look up the Oaxaca.
My hunch is that a lot of this is actually the fact that the models aren't taking the dependence
Yeah,
among the
I don't know, so I don't know
regressors.
what, so I can't answer.
Yeah, no, I don't know for sure, but.
Yeah. So the thing that's bothering me is that I'm thinking back to some of your early pictures. At some point, it's going to be very difficult to tell the difference between a linear model with an interaction and a nonlinear model.
Yep.
And so I'm wondering how much of this could be accounted for by just being more careful about checking residuals for a model.
That's more or less what I.
It seems to me, or even just doing more graphical analysis before fitting this standard linear model with an interaction. I mean, it's a nice illustration of what can happen if you're kind of lazy and jump right to the data analysis, but I'm wondering how it relates to some of the other things that we should be doing.
Just diagnostic. Right. So I haven't done that. When I was doing the U-shape paper, a lot of people had that reaction. So basically, a lot of the reactions I'm getting now, actually, they were way more severe with the U-shape one. They would be, we know this, there's a better solution, and people wouldn't do what you're saying they're doing. And so one of them involved, they wouldn't do what you said they're doing because they would do diagnostics and whatever. And so the thing with diagnostics is they have 2 problems, diagnostic blocks. One is that if your R-square is very low, there's going to be so much noise, it's going to be very hard to detect anything. And in practice, our R-squares are very low. But the other one is, they tell you the model is right. They don't tell you your inference from the model is right. And because all models are wrong, usually diagnostic will look bad in a non-diagnostic way. It will look bad so if I did it, for example, if I did the diagnostics on the square thing, they will look bad. But the diagnostic will tell me the world is not quadratic. And I'll say, I know that. What I want to know is my attempt to figure out if there's an interaction correct? And the diagnostic plot is not going to give me that. But that's I'm extrapolating from the U-shape. I haven't done it here. Maybe it is easier to use the diagnostic from. Do you find you're okay with that? Or?
Yeah, I'm okay with that. What's bothering me more is just in terms of choosing the more plausible model. It's a matter of...
You mean what's more plausible? Linear with interaction or quadratic?
Right.
So that's one thing that
Or
really
not quadratic, linear with interaction versus some sort of nonlinear, not necessarily quadratic.
So that's something that when I talk about Ganzak, I say great things about him. One thing I really like about that paper is he says, look, it's basically a collinearity problem. It's hard for us to tease apart xz from x squared. And so he says, but we don't have to take a data approach to it. We can take a principal psychology approach to it. We say, just think about what is linear in psychology. And if you can't think of many things, your default should be, I will control for nonlinearity. And so if you think about perception, Weber's law. Right? So perception might be like this. Incentives, decreasing my utility, increasing marginal cost. If you think about Likert scales, they're going to have ceiling effects. Almost everything we measure, we have very, very strong prior beliefs that they're not linear. And so if it's a tie, you should err on the side of it's not linear, and there's no interaction. And that's not my argument, that's Ganzak, but I'm completely persuaded by that. So that if you don't have data to reject that null, you should go with it's not linear, and so we don't have evidence for the interaction. But that's, it's a personal, it's a subjective thing. It's not math.
Sense. It's just a power issue then. It seems that in most cases there's so little power that you wouldn't even.
Yeah, I don't know. So it goes back to the issue about why aren't you getting the interaction? So how to put it? Yeah.
I think my question's more just like applicability. So I think one of the things that we're getting at is more complex interactions and kind of understanding like their underlying form and things like that. And with my research, oftentimes what I'm looking at is at least I'm looking at 4 different variables that will be entered in and looking at the interaction between all of them, which may vary in a lot of different ways, right? So it's always at least going to be age, education, ethnicity, and gender, always, right? So I think just in terms of like applicability, like what can I take away from this with like, how can this can be applied to more complex situations?
I think it would be, as long as you don't enter like three-way interactions, because all of them are interactive between 2 variables. This is nice in that you would only add 4 variables to your regressions. You wouldn't add many more, like you wouldn't need to add all the combinations or something. You would say, because it's age and gender, I'm gonna throw in age squared. With ethnicity and gender, I guess you don't have to worry because there's no linearities to worry about. It's just a box. So from the ones you mentioned, so it's gender, age, ethnicity,
Education.
and education. So education and age would need to be squared, and that's it. And you're done.
That's so much easier than what we've done. Sounds way better. Okay.
When I say you're done, I say in terms of being confusing a nonlinearity with
Yeah, I think my other question to follow up with that was just like in terms of power and feasibility with like data collection, like, I think if making an assumption that I can just do like this quadratic addition or whatever to my formula is like much simpler, it's more feasible.
Yeah. Okay, great.
Thank you.
Happy to hear that. Yeah.
Will your idea yet last night can be incorporated into this one to avoid this problem of p-hacking as well? Because in my experience, many of the moderation analysis were purely exploratory. They say, I have a main effect, I have collected age and gender, they are always collected, and then, let's try a moderation.
Yeah.
Do you think that pre-registration and all these techniques you study will help?
Yeah, I mean, I definitely wouldn't. I would be much more skeptical of an interaction that was not pre-registered because there are so many ways you can do the interactions, and because the interactions tend to be largely independent of the main effects, that it basically doubles your chances of getting significance. So yeah.
So is your pre-registration of analysis is going to get to this level of detail? In other words, I'm going to deal with interaction by using splines versus,
So right now it's to the taste of the person who's fulfilling it. We're toying the idea of a better system of having feedback. So we would have a scientist who's not a social scientist to help us about scooping, reading your registration, and giving you feedback, like if automatized. So you check the boxes. It would say something like your analysis is insufficiently specific. Try this. Right now it's kind of free flowing and people are doing whatever.
Okay.
I would say people tend to err on the side of too many details, not too few.
Okay.
So far I think that's the way to go.
Is that your simulation is involved the sample size?
Yes.
Probably.
Yes.
There are two samples.
Yeah. For the false positive there's 2. For the power there's 1. And it's a sample size that will give the quadratic test 50%. So I before I run each scenario is 2700 I think, is run a certain number of times. Before I run them, I figure, okay, what sample size do I need to have this power, and then I run. Because otherwise you end up running a lot of simulations that don't have any values. The power is 6%, who cares? Yeah.
This is sort of an applied question, actually, about planning for studies, right?
Yeah.
So if the case is that you're trying to sort of do a power analysis for a proposal,
Yeah.
and then you're thinking through the specifics of your analytic model, right? And you had previously anticipated just running an interaction effect, which is going to compromise your power. So if you're low sample size, you may not detect the effect, right? So you have to power up for just a regular interaction effect. But now you're adding additional variables to the model. So that requires different power computations, right? I mean, you would essentially need more sample size.
Not always. So Gansak has a couple of, I mentioned there's 4 papers that have talked about this. None of them have done large-scale simulation. They have chosen one example and shown how it changes with quadratic, and said, see, it seems kind of better with the quadratic. But some of those examples he has, you could increase power by throwing in a square term when the square term is working in the opposite direction than the interaction. So it's so it is trickier to do power because now you have to make even more assumptions. I'm kind of skeptical on power analysis for that reason. I don't think you can ever have enough information to make it meaningful. But let's suppose you're not in my camp. You're in the camp that you believe in power analysis.
Well, I'm in
Can
the
we tell
camp.
that to grant reviewers?
Yeah,
I'm in the camp of
That's my
federal
camp.
grant reviewers.
Right, absolutely. Right, but then you do what a lot of people do, which is, okay, what sample do I have? 200. Okay, what assumptions lead me to 200? And that's,
Sure.
you ask a research assistant to your power analysis that justifies your.
Yes.
That's, I think,
I guess what I'm
73%
asking
of power
is in
analysis.
thinking through the power analyses for a grant proposal, it would seem to make sense that you would want to account for
You would want to account for
additional
it.
variables in the model
Yeah.
that are going to, all else being equal, compromise power, right? Reduce your degrees of freedom.
Yeah. Yeah, but the thing is that, so if I believed in power, okay, let's start with this. Let's assume I believe in power analysis. Of course I believe in
Just
it's math.
pretend you're a grant reviewer.
Yeah.
They want to see a power
No, because
analysis
if it's
section.
And they don't think you have a big enough sample.
Okay, so you're saying-
It's required.
You're saying, no, I know. So you're saying, I'm with you, you're saying, I'm with you.
Yeah.
I don't really believe in it, but
No.
what do I write if I want to have a square term in there? So I think it's, whoever's doing the power, so whoever's going into G power now, I think they could easily add that, and then what they're going to need to add now is some assumption. So it's going to some assumption about. Actually, I'm going to take that back. G power would not be good enough because G power won't allow you to tell it that there's some sort of specification. And so G power will assume that the reality is linear if it's linear and the reality is quadratic if it's quadratic. So you will need to, in practice, you will need to either assume, okay, for your grant proposal, what I would do if I had to do it, I would say I'm going to assume it's truly quadratic. And do the power calculation that G power tells you, and play with the numbers so that you come up with a reasonable excuse for the bureaucrats saying no in the power. That's what I would. That's my candid advice. You know.
I just have one
say
more
that's
question.
a conservative approach, kind of. Like that's your rationale. It's like, oh, this is conservative that I'm using a quadratic. At least I will have enough power. Like using a quadratic formula, I know. Like I'm rather confident.
Well, I was talking about a scenario where you're pressed on what are the degrees of freedom that you're assuming in your model, right? And so you have to actually specify
No, so,
what are
so in
the
that
inputs
sense,
in the model
it
to
should,
that
I mean,
degrees of
whoever's
freedom.
reviewing should like it, because you're telling that person, I'm relaxed in these arbitrary assumptions of linearity.
Right.
So that's going to give you like brownie
Right.
points, right? So
Yeah, I just have a quick follow-up question, which I think relates to the power, but I'm not sure how. Which is, so does all of this apply if your interaction are cross-level interactions in a multi-level model frame? How,
I
or,
think
or,
so.
how do you?
I think so.
I guess the question is, how do you think about that?
So-
If X and
So I don't
Z
think in multi-level
are
very
different.
much. I know it exists, and I have some familiarity with it, but my research doesn't come out. So, but I understand the logic. You know, they have classroom and students. I understand that. And so I think it's the same.
Yeah, in my case, literally.
Literally, yeah. So I think it's the same logic. But that's actually why I like the quadratic over this spline. Because when it comes to like spline world in multi-level, now all this prepackaged software became, I can't use it, because how do I cross that with it, as far as I can tell? Unless you're using like, maybe there's an R package for it, but if you're using SPSS, probably you can't do it. And so, but if quadratic, you can. And so in terms of usability, there's a big benefit of sticking to what you know, plus a little bit of extra.
Yeah, I mean, just a quick follow-up thought, which is, if this approach does end up making some compromise to, or some greater requirements for more sample size to balance out power, it would do that even more so in a multi-level model, right? Where you are having to add a higher level quadratic term, you know, so
I don't have intuition for that. So.
Yeah. Thanks.
You have to be really careful with random slopes, though.
If you have spline.
Well, even if you had the quadratic, you'd have to be really careful because
With the conversion problem.
because quadratics are going to be really correlated with the linear terms.
Any more questions, comments? Right, thank you very much.